Hey, what's up? So today I want to talk about vectors and matrices. In other words, that's linear algebra. By the way, Luckman, is that you, Luckman? Anyway, I'm gonna minimize this, I guess. Yeah, sure. All right. So vectors and matrices, linear algebra. What is all that about? And let's give it like a crash course, sort of silly explanation first. Here's a vector, right? It has a tail. Do you call it a tail and a head? I guess. And yeah. So you can imagine it as a pointer somewhere in space. Here we're looking at 2D space, I guess, because this is flat, but you can imagine a 3D version of that. We could draw somewhere an x and a y coordinate axis. Now, normally in linear algebra, we think of all of the vectors as having their tails at the origin. So in a linear algebra context, this is not exactly how a vector works, being out here somewhere. But there are other contexts where, well, there are other ways of thinking, I guess. You could imagine a vector out somewhere. But when we do linear algebra, we imagine that we first take this vector out somewhere, and all the vectors that are anywhere, we bring them all so that they start with their tail at the origin. And we'll get into more details about what that's about. But I suppose for now you could say it's partly about comparing vectors. For example, if we had over here a vector of the same magnitude, meaning the same length, and let's say, let me make it up here somewhere, okay? Same length and kind of the same angle in a sense. It's running parallel. Imagine that. Well, when we do this process of bringing them all to where they start at the origin, the tails are on the origin, then we can make the analysis and say, oh, these are the same vector. If the direction is parallel and the magnitude is the same, the length, then they're describing the same vector. Even though naively you might say, oh, look, these are two different vectors because they're in different positions. I suppose that's one way of thinking, but it's not the normal mathematician's way of thinking or the linear algebra way of thinking. But yeah, when you do physics, for example, you could have two vectors. Say there's an object here, and we have two vectors. I tried to make that the same length. So say we have two vectors equal and opposite. Then there will be no net motion on the particle. Let's say there's an object here. Okay. And if these vectors are equal and opposite, then the net force, it would be zero. If we were talking about force, and vectors don't necessarily have to do with anything with force. But when you learn physics and you learn sort of your physics 101, basic physics, you might call it kinematics, like objects moving around and bumping into each other and all that stuff. One of the first things that comes up is the concept of a force. And vectors are used to talk about forces. So, but that's, yeah. But in the mathematician context, we always think of them as starting from the origin. And so I suppose at this point, for a lot of people, this might seem kind of confusing, but don't worry too much about it. It'll make sense as you go and as you learn kind of more contexts in which vectors are used, then it might make more sense. Okay. So there are a few ways of talking or thinking about vectors. So the first way is kind of this basic naive, I'll say naive, but I don't mean it in a bad way, just the beginner's story of these. They're kind of like pointed line segments. The key thing is that they have a direction and a magnitude, a direction and a length. And so they're just kind of pointers in space. Naive perspective is that they're pointers in space, basically. So you could talk about a 2D. You could talk about them in a 2D context or a 3D context or 1D or 5,000 dimensions. It doesn't really matter. Okay. I forget. I think there's like this other middle context that I want to maybe talk about. I forget exactly, but maybe there's a second one in here. But there's definitely a more advanced one, which is the math, or anyway, the linear algebra view. I'll just abbreviate linear algebra. I'll write it out in case for some people who, maybe English is not their native language, they would like it to be written out. Linear algebra. That is the sort of the subject here. The math is the broader field, I guess, but it's, to be more specific, we're talking about linear algebra here. When we talk about vectors and matrices, linear algebra makes it sound like it's something simple, but this is college level math. In fact, I think the first textbook on linear algebra was in the 40s or 50s. And I do want to talk a little bit about the history of the subject. Anyway, but yeah, so it's fairly advanced mathematics. Okay. Now, so when we get to this mathematician's definition here, it's going to seem a little overwhelming at first. I'm going to simplify it for you, but there's actually kind of, well, I'll explain it like this. So what are vectors from the technical point of view, this third advanced way? Vectors are elements, so I'll write this out. Vectors are elements of a vector space. So for a lot of people, this definition doesn't really help, right? It just makes you think, well, what exactly is meant by elements, and what exactly is a vector space? And that's where there's 9 definitions of a vector space. Or 9 requirements, basically. 9 kind of parts of the definition of a vector space. Elements are just like elements of a set. Same thing. So in math, you can have a set, I don't want to belabor this too much because it's really simple. You can have like the number 1 and the number 2, for instance. That could be your set. There's also an empty set, which I think is just denoted. I have trouble writing this on the computer. I think this is the empty set. Sometimes it's written like this. So a set with nothing in it. We could have a set with, you can have negative numbers, imaginary numbers, all kinds of different things in a set. It's a very general mathematical concept. And there's something called set theory, which most people don't dive too deep into it because you just need to know some it's really, what most people know is just notation. Like there's I think, so this symbol is the intersection of 2 sets. So you have a set A, like this could be A. And let's make this 2. You know what? Let's make this, okay. Let's make a new set. B is 2, 3. So intersection AB is going to be, the intersection is, this is like an and the way I remember that is in the word and, you have this N. The N part looks like this. So I imagine it as an N. But and intersection also has this N. Both of these words, they have N as the second letter. If it's and or intersection. So hopefully that can help you remember. Because there's the next symbol is going to be this, which is the union. But so I want to actually erase this in thing I wrote. So A union B. So the intersection of this set A and B will just be the set 2 of with the number 2. This is the only element of the set. And if we're doing the union of these two sets, it will be sort of the sum of them. This, you can say, map as or, and this is sort of and. So if an element of these sets is in A and B, then the only one here is the number 2. 2 is the only element that is in both A and B. And if it's A or B, well, we have 1, 2, 3. So, you can call this elementary set theory, and set theory sounds fancy, but it's very rare, I think, that people, even if they're majoring in math, that they take a full class in set theory. But you can go deeper into the axioms of set theory. It almost becomes kind of philosophical, because this is really foundational in mathematics and gets into foundations of math that I know almost nothing about. But there's just this sort of basic set theory, which is this kind of basic notation stuff, which frankly most people can learn in a day or two, or even quicker. You can just look online, basic set theory, and you'll get a bunch of definitions. And frankly, most people learn it just sort of as they go while they're learning other math in general. So I don't know if there's a limit to how much I can undo. I just want to clear it. Yeah, it won't let me go that far. Okay. So while I'm erasing this stuff, oh god, it's erasing like that. So I want the black, and I want to go big. Oh, pen. So so it doesn't. I need a better solution. Somebody help with a suggestion. This is not good enough. I can make a rectangle, huh? No, I can't. You can't even make. And you know what I can do? Rectangular selection. I can. Oh my god, no. Remove this, and then I can. Oh, there we go. Okay. All right. Vectors are elements of a vector space. So we talked. I mean, if it doesn't make sense to you what an element is, this is just the same as an element of a set. Then review everything I just said about sets, because the word elements came up a bunch of times. So when we define a vector space, we start with a set. Okay. And what was I going to say? Yeah, so it's almost like we define the vector space first, and from there, that makes the elements into vectors. And what I'm going to do is, I forgot, I need to find those 9 requirements. And so I'll edit this video probably. But the 9 requirements, I want to make them simpler. So there's an easier way of thinking about it, which I'll briefly talk about. So when in math and physics, oh shit, it's an earthquake. Okay, I'm back. So there's these, I was saying 9, but some maybe counted as 10 requirements for vector space. But I'm going to make this all very simple and basically boil this down to really, it's really 1 or 2 things, in a sense. I mean, if you listen to mathematicians and physicists, it's extremely common that they'll talk about vector spaces very casually. Oh, that's a vector space, or you have this vector space, yada, yada, yada. It's part of the language of math. And I immediately think 2 things. There's basically 2 things that means to me, to boil it down. So we are going to go through these 10 things. I don't have these memorized at all. You don't need to memorize them. But we're going to go through the 10 things and explain how this boils down to really 2 basic ideas. It's all very intuitive, actually. And the power of this definition is that it basically allows for abstract vector spaces, which are just vector spaces. but like there's more types of vector spaces than this naive story with pointers. And that's very powerful. And so that is the benefit of doing this. But if we want the technical definition of a vector, this is what we need to do. Now, you can become a pretty good game developer, I'm sure, without knowing about this. However, I think it's definitely an advantage to know what vectors are in legitimate mathematics, because if you're searching online, let's say you want to do your game development stuff, and you're just searching around randomly online, you will run into discussions of this. And so, if nothing else, just so that you're not totally confused when a proper mathematical discussion involves vectors, it's worth learning, which we're going to do today. And I want to say I got this list. I mean, let's see, just looking on Google Images for vector space, there's a bunch of different ones, and I just grabbed one. Unfortunately, it doesn't scale very well. I sharpened the image. I know it's not going to come up very nicely for some people, but I'll be rewriting everything here. Okay. And before we go into these 10, I want to summarize, and this might not mean anything to you yet, but there's really two things here. Okay, there's two things that this is all about. There's scalar multiplication. Just write this, scalar multiplication and vector addition. When you tell me that you have a vector space, this is what I think of. Oh, okay, you have something with scalar multiplication and vector addition. And we'll also describe more of why that's important and all that, but okay. Now, looking at the naive, let's look at the naive picture here. Scalar multiplication, again, we think of the vectors as starting at the origin here, so we'll again describe that more, why that's the case. But we have you can imagine all possible vectors coming out from here. I can't draw all of them, but basically any point on the plane, including the point 0, 0, all of the possible points have a corresponding vector associated with them. And all of those have a certain magnitude. You can calculate the magnitude. It's basically the distance formula. So I'll write it with D though it's really magnitude. So let's write it with an M. But it's the same formula as distance. In this case where we have a two-dimensional vector space, and if we choose to label this with X and Y as these components of the vectors, then this will just be the magnitude of a vector. Let me write it like this. The magnitude of a vector we normally write. So a vector this little symbol on top emphasizes that this is a vector. There's different ways to write vectors, and different textbooks will do different ways. This is one way. And if I go like this, kind of absolute value signs indicates the magnitude. And it's the distance formula. Since we're in 2 dimensions, it's basically this. I mean, there's many other ways to label things. Like you could label this. Unit vectors are often labeled with an E, because if we're talking about more abstract things, X and Y might be a little confusing. The more kind of general way is E1, E2, E3, E4, etc. And this is just notation I'm going over. The concept is the same. The magnitude. Now, I wouldn't write E1 squared here, because that's referring, this E1 squared E1 is referring to the unit vector. We'll talk more about what a unit vector is, but, well, a unit vector is simply, so if this is X and Y, I know many of you know this already, but it's a magnitude of 1 in the x direction is the x unit vector. We often denote x hat. Okay? I'll write it as a column vector, just notation. 1, 0. And y hat is a 1 in the y direction, or it's a vector in the y direction of magnitude 1, length 1. Magnitude 1, okay. And it's going to be a 0 for the x component, 1 for the y component, okay. And, okay, so with this notation, what we typically do is that I would write it like this. There's different ways. We could just do a v1 squared plus v2 squared. It's just, again, notation. The important thing is that you understand the overall concepts. If this is totally new to you, I don't expect you to understand everything yet. But sometimes think of things as learning a language. You have to get exposed to certain things. You have to maybe see examples before things make sense. So here, I'll give you two notations. It really doesn't matter which one. The longer version, you can write this out as v1 e1 v2 e2 if you want to. Normally we wouldn't. Normally we'd just write v1 v2. But as you get deeper into math and physics, in certain contexts, it's important to remember that when we write this v1 v2, a vector is really so I'm jumping ahead a little bit. I'm getting a little technical in my language, so I apologize for that. But don't worry if this makes no sense. We'll explain it later. A vector is a linear combination of, what's this? I don't know how to explain it exactly. But it's, these are, the v1 and v2 are the components. Okay? And yeah, I don't want to be too overwhelming. So maybe I shouldn't have really gone into this, but there's different ways of writing things. And yeah. So even if you only write the components, components by themselves are not, kind of technically speaking, they're really not enough to describe what a vector is. It's the components times the unit vectors is a more technically correct approach, in my opinion. But what do I mean by times? So yeah, there I'm kind of at the limit of my teaching ability because I'm thinking dot product, but is that true in general? I'm not sure, so I shouldn't be talking too much about that. Let's get back to this stuff. And so some of you, again, probably getting confused, but we have scalar multiplication and vector addition. So scalar multiplication means that we scale a vector. So I'm going to remove this vector. I'm going to move it to where its tail is on the origin. Okay, so first I'm moving this away so that the tail is on the origin, because we always do that in a technically correct math context. So now, here's the same vector. Tail is now at the origin. And if I'm scaling the magnitude, then let's say if I multiply this vector, let's call it v. If I multiply it times the number 2, I double the magnitude. So this is going to be 2v. I can also do minus v in the opposite direction. And minus 2v, this will be minus 2v. This is scalar multiplication. It just scales. But you notice, and so I can do like 1.5v. Here's 1.5v. You'll notice that no matter how I scale, no matter what scalar I multiply, by. So this ordinary number that we multiply the vector by, we call that a scalar. It's just a number. No matter what number I choose, it will always end up along this line. The head of the vector is always going to be on this line. Even, it's okay also to multiply it times 0. It's also worth knowing that, so this will equal the 0 vector. It's worth knowing that there's a scalar 0 and there's a vector 0, and these are two different things. The vector 0 you can imagine just as this point at the origin, basically. The scalar 0 is this 0 number. In most contexts, this distinction is not really important, but things might get confusing one day if you don't make this clear. There's a scalar 0 and there's a vector 0. And normally the vector 0, even people just write as a 0. But so you might want to, in some contexts, be clear. Are you talking about a scalar 0 or vector 0? Vector 0 in this is a two-dimensional vector space. The vector 0 has these components, of course, 0, 0. Okay. All right. And so that's scalar multiplication. That's our intuitive picture. And we're going to have vector addition. Vector addition is a common graph you always see for this stuff in math textbooks. You have two vectors. These are two different vectors. Notice I started both of their tails at the origin, like we do. When I add them together, so I can take this vector over here, and we add tip to tail. So if I start here and I add, let's call this A, B. Okay, A, B. I start here and I do the same vector A. And now we get this position here, and we can talk about this vector C. Okay. Vector C, I'm saying, is A plus B. And this is just the graphical representation of what adding two vectors looks like. You have some A, you have some B. Now we could have, it's commutative, we can do it the other way. We can start with A and then add B. Here's B. And here, this was A. So you can see there's kind of this, there's basically a parallelogram that forms. Okay. It's a parallelogram. A. And it doesn't matter about the order. They add up to form C. Okay, that's vector addition. This is the sort of graphical representation of it. It is good to learn about this stuff in math class, and you get more practice and actually get practice adding vectors and stuff, so it becomes very second nature. But for now, that's all I'm gonna say about vector addition right here. It's fairly straightforward to me anyway, but I have a lot of experience with this stuff. But these are really just the two things. When you tell me you have a vector space, it tells me that you have a set, and that for all the elements on the set, you have defined scalar multiplication, and you have defined vector addition, and it works together. And there's this thing called closure, which we'll describe, but this is rather obvious to me. This is like, I don't even need to think about it. But we'll get into these. I don't know if they're called, yeah, they're called axioms. So axioms are kind of, I don't know how to explain it. It's your, but anyway, these are the things that describe a vector space. So let's talk about the first one. So let me just move this over here. So the first one says, okay, actually, let me read this text in case it's important. I don't know if it will be. A vector space is a non-empty set V of objects. So non-empty, so we don't have the empty set, we have actual elements in our set. Okay, a vector set is a non-empty set V of objects. Now, why do they say V? They're going to use V later, so that's all. They're just introducing that. Okay. A vector set is a non-empty set V of objects called vectors on which are defined two operations called addition and multiplication by scalars. Subject to the 10 axioms, or rules, listed below. The axioms must hold for all vectors u, v, and w in V and for all scalars c and d. So all these letters are just chosen arbitrarily. You can use whatever letters you want. Okay, don't worry about the letters if that's confusing to you. The key thing is that we have these two operations, addition and multiplication by scalars. So, but they didn't say it here. They didn't say addition of elements, but I prefer that language because I prefer to specify addition of elements because you could get confused and think I'm talking about addition of scalars. Okay. Okay, so number one is this. So these u, v, and w lowercase are vectors, okay, in this vector space. So the first axiom or the first rule or requirement here is that the sum of u and v, denoted by u plus v, is in V. So that's closure under addition. So it's just saying that when we take two vectors and we add them together, whatever that equals, it has to be an element of the vector space. So I'll just pick an arbitrary letter. I'll just say, let's say this is Q. Then I'm going to say this means that Q is an element of the vector space. And that's this picture here. So if for some reason this vector C that I represented here, if for some reason this were not one of your elements in the vector space, then that would be strange, right? So as we're going through these examples, I want you to think of sort of concrete pictures or concrete examples and run it through your head and make sure that it makes sense to you, what we're saying makes sense. So the obvious examples are the two-dimensional vector space and the three-dimensional vector space. So I'll try to make more of a technical definition. So let's say let's say big V. I'll write like a 2 subscript. This is not how we normally denote the two-dimensional vector space. Normally we write it as R2 if we're talking about real numbers. Okay, but we haven't really explained that, so that's why I'm starting like this. I'm saying, okay, V2 is a set. I don't know if I'll be able to do this in the technical math way. I'm not that good at technical math stuff. Let's say I'll just write, we want pairs of numbers, A, B, such that, I think I can just do a colon. A and B are, let's say, real numbers. You can do other things. You could do natural. Well, see, natural numbers is not going to have closure because you don't have like a negative number. And the scalar multiplication involves, like we saw, going into negative territory. So natural numbers are not going to work. Natural numbers, by the way, are so like the whole numbers, but they include, they're basically the whole numbers, I think, but they include 0. Pretty sure. I'd have to check that out. But AB, but there's also complex numbers if you know about those. So it can be other things. And in fact, I think you can do the rational numbers, I think would be okay. I'd have to check though. But some people look at these things. Don't quote me on it. I'm not sure. I could be wrong. But anyway, this... for our purposes, let's just focus on the real numbers because... I don't want the focus to be on this part, which... This part is what we call a field. and I don't want it to be the focus. We kind of assume that there's a field. They didn't use that language here, but I bet you we can find a different one that talks about a field. Let's see if we can do that. It's a bunch of different things here. Is this the one I was looking at? Yeah, this one does it. A vector space over the field K, or simply a K vector space. So what are fields? Well, you know a field, the real numbers is a field. If you know the complex numbers, that's a field. I forget if see, I'm always dealing with real numbers, complex numbers, maybe even I'm looking at quaternions, but that's not a field because it's not it's not commutative. So basically, real numbers are fine, but some people are really focused on like rational numbers. Okay. So some people who are viewing might not know the difference, like exactly what is meant by a real number. So let me describe that, and then we can get back to this stuff. So let's start with the rational numbers. Actually, let's start with some numbers that you're probably familiar with, like square root of 2 and pi. If you're not familiar with these numbers, then I'm sorry, you just have to go out and learn what these mean. Pi is a transcendental number, but so what these two numbers have in common is that their decimal goes on forever and it does not repeat. Okay. I think this is it 1.41 something? There's no pattern in the decimals. So for example, if you have 1/3 is basically, I'm almost tempted, I'm going to write an equals sign here actually. 1.3 repeating. The 3's go on forever, okay? Normally we just write this like this. And I did that wrong. It's 0. Not a 1. Okay. 3's go on forever. And basically, if a decimal repeats itself, if there's, let's say, it's 0.532, and then 32, and then 32 forever. So it's, in other words, it's 5, some bunch of numbers, it could be anything. Let's add a 1, just for demonstration. If you have some numbers here, and then these repeat forever after that, then for sure, it is known that we can describe this as some ratio of two whole numbers, basically. Okay, so that's those are rational numbers. This is a rational number. We denoted the set of rational numbers with this Q with a line through it. Whereas these numbers are, well, this is an irrational number and the other one is a transcendental number. I'm not too clear on what the difference is between irrational and transcendental. The number E, no connection with these unit vectors that we labeled as E, but the transcendental number E is a transcendental number. Okay. And so, but the real numbers, we start with the rational numbers and then we add in these other ones. The irrational numbers and the transcendental numbers are added in. And that will give us the real numbers. Okay. Now, there's lots of videos out there describing this if it's confusing. You can think of it as all the possible decimals, including all the possible decimal numbers, including the ones where the decimals never repeat. Now, there can be a pattern, for example, let's do 1 0 1 1 0 1 1 1 0 1 1 1 1 0. There's a pattern, right? The number of ones is increasing. It was 1 1, 2 1s, 3 1s, 4 1s. That's a pattern, but this is not a rational number. Okay. So whether there's a pattern or not, I feel like there's always going to be some kind of pattern, but maybe not. I guess that's not necessarily true. No. But anyway, you can imagine the real numbers as like all the numbers with whatever, all the decimal numbers, whatever the digits are, whether there's a pattern or not, whether it's repeating or not. Those are the real numbers. That's how I think of it. Okay. And that's what we're going to be dealing with primarily. Just as an example. But so this is the word here is that it's a field. But that's not really important. You don't really need to know about that, really, for our purposes. Okay. So we had the first requirement was that we have closure under addition. It means that when we add two vectors, we get another vector, which is also an element of the vector space. If what I just said doesn't make sense, go back, listen again and again until what I just said makes sense. Might take a few times. Okay. All right, now we have the second requirement. Now, what I want you to do while we go through all these 10 requirements is I want you to look back at what I said, that a vector space is really about these two things. There's the scalar multiplication and there's addition of vectors, that these two things are defined. So I want you on each of these 10 to look back and think about it, that for you, in your head, if you have these two things, does that imply these other 10 things? Because for me, these other 10 things are obvious once I assume these two things. So this is just a mental model for me to simplify so that every time somebody casually talks about a vector space, I don't need to think about these 10 requirements. It's much better to focus on these two things rather than 10. So as we're going through here, compare this to the two things, scalar multiplication and vector addition. For me, closure, like I said, is obvious. This picture. Obviously, you're going to get another vector. As long as you've chosen, if you've chosen a set, right? First, we start with a set. If you've chosen a set that makes sense, that looks like a vector space, okay, then, like not a really dumb set. Like you could take all of the points in the two-dimensional coordinate plane, except not this point. Well, now you're not going to have closure because certain things add up. Like I could choose this vector and like this vector or something, and when you add them together, you get this vector. So you get this vector that I just removed, and that's not closure. So you did something very silly. Why would you remove this one point? Okay. So this is commutativity of vector addition, that u plus v equals v plus u. And I already talked about that. To me, this is obvious from this picture of vector addition. So again, given our two things, scalar multiplication and vector addition, this is obvious to me. And I hope you feel the same. Now we have this associativity, so u plus v parentheses plus w equals u plus v plus w. These are all vectors. I'm getting lazy about the hats, and you find pretty much in all contexts people get lazy about, not the hats rather, but the notation. I don't really, by context, hopefully you can see the difference between a scalar and a vector. But we're talking about vectors here, u, v, w, and I mean, there's probably a diagram. You can probably draw this out. Let me think. Do I want to do that? Diagram is going to get complicated, I think. Let's see if I can do it. So let's say this is u plus, this is u, here's u, here's v, this is u plus v. I know the u's and v's kind of look the same sometimes, but this is u plus v, then we're going to have w. So let's say W is here. Let's make W here. W. So we do U plus V and then plus W will be here. But if we do V plus W first, where's V plus W? This is V plus W will be, let's see, here. This is a W. So this is, remember the origin. Here's the origin. So we did V first, then W. And then we need to add U, which is here. U will bring us here. So this is the same spot. This doesn't matter. This is associativity. So there are these kinds of graphical representations. I don't know if that's the best way to think about it. But I'll just say this is totally unsurprising, right? This is normally true with addition. So totally unsurprising. Like I don't even need to think about it, to be honest. Number 4. There's a 0 vector in V such that U plus 0 equals V. So I talked about the 0 vector. Or sorry, U plus 0 equals U. I think I said that wrong. This is not hard to think about. If you have a 2-dimensional vector space, 0, 0, whatever. It's not complicated. Number 5. For each U in V, there is a vector minus U in V such that, okay. We talked about that. Also, so if you have scalar multiplication, it includes these negatives. This will equal the 0 vector. Not the 0 scalar, but the 0 vector. These are all vectors. Okay. To me, from what I described before, it's obvious. Number 6, the scalar multiple of U by C, denoted by Cu, is in V. So C, some scalar now. Let's use S for scalar. S times U. Now I'm being careful. I'm putting the vector notation on U. U is a vector, S is a scalar. The scalar multiple of U by C, denoted by Cu, is in V. So this equals something where V, this is basically closure, right? It says closure under scalar multiplication. This is an element of the vector space. So what this is saying is that when we scale the vector, that's also in the vector space. In other words, when you multiply times a scalar, it's still in the vector space. To me, saying scale the vector and multiply by a scalar, that's the same thing to me. Thus the word scalar. So we talked about that with this vector V. I multiplied times scalars and showed that it's always going to be on the same line. Basically, it has the direction is maintained, as long as you're counting the 0 vector as the same direction, which is maybe a little strange and wrong, maybe, but you get what I'm saying. Roughly speaking, no matter how when we take this V and we multiply it times a scalar, the direction either stays the same, that's including, it could be in the opposite direction. I'm including that as being the same. Or it could be the 0 vector. But all of those vectors are still in this vector space that we described. Okay, so closure under scalar multiplication. I'm running out of space, unfortunately. I should have made this canvas bigger. Then we have 2 distributive laws, which again, you know, when you learn the laws of, I'm going to use an S again, it's for scalar. When you learn the laws of algebra, I don't know if the laws is the right word, but when you learn basic algebra, you know, distributive property is one of the things that you learn. So there's nothing surprising here. This scalar will distribute. It's almost better to point out what is missing from all of this. What is missing from all of this is a way to multiply 2 vectors. Now, there are ways to multiply 2 vectors, but they're rather advanced, actually. So it's going to have to be another day. And in fact, basically if you take a linear algebra course, we talk about the dot product and we talk about the cross product. These are, I don't know how technical I want to be. These are things, I'm not going to get too technical. I'm just going to say these are things you can do. But basically, we're not talking about that yet at all. Multiplication of the vectors is totally missing from this whole discussion. Now you can multiply scalars just fine. Just they're regular numbers, the scalars, so no problem there. But that's also really important to point out that multiplication of the vectors themselves is missing from all of this. It's not defined. That's really important. Why is it important? I guess you get to the question of why do mathematicians define things the way that they define them? It took a really long time, but people figured out that by having this definition, it sort of extracts a really important, the essence of something really important that you see in many, 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 many different contexts in math and physics. So it took a long time. It takes often a long time to figure out what is the definition that really extracts some really important information where we can look at structures and figure things out, figure out really important patterns. So that's why the definition purposefully, multiplication of the elements of the vector space, multiplication of vectors, is intentionally missing from this, and that's important. It allows us to extract, to make all kinds of conclusions about vector spaces that we would not be able to do otherwise, because if we added multiplication of vectors, we would be getting more specific and less general. And you might say, well, what about more general things? There are more general things. For example, we talked about the real numbers as a field. You can just talk about multiplying and adding scalars, for example. That's a field. There's other things called, so there's a field. There's another thing called a ring. This is called abstract algebra. There's another thing called a group, which is super, super important. There's a bunch of other things. There's semi-groups, there's monoids. There's a bunch of things in abstract algebra. The most important is group. Vector space, I don't know. Vector space is almost so important that it's basically has its own separate domain. It's linear algebra. I don't see, you could throw in vector space as another object of interest inside of abstract algebra. So abstract algebra is a college level math course. Okay. Fields, rings, groups, monoids, semi-group. There's a bunch of stuff. But anyway, most important, definitely vector spaces, definitely groups, and fields. Fields are pretty simple. Because you're familiar with it, you know the real numbers, and that's a field. The complex numbers are also a field. Groups are super important. That's like the main subject that you learn when you start an abstract algebra course. Sometimes there are courses just on group theory. And vector spaces, that's all about linear algebra, so those are super important. So there's ring theory, whatever. Yeah, there's a bunch of other stuff. Okay. S, let's be careful to say these are vectors, while S is a scalar. So this is, to me, totally unsurprising, this little law. We can go the other way. So we can go U, that totally looks like a V. U plus V. We can multiply on the right. And the scalar multiplication is commutative, so, but I'll write it on the right side here. But you can multiply on the left as well. Doesn't matter. If S is from the real numbers or the complex numbers, this is true. But see, if S were a quaternion, it would not be true. Those are not commutative. So that's why we don't normally, we kind of put quaternions in a separate box, separate category. Yeah, so this is true to me. Again, this is super obvious. This is number 8. Number 9, and so we just have 2 more. Number 9 is associativity. So associativity of multiplication, but here it looks like D is also a scalar. Equals again, super obvious. And number 10 is that 1, I'm going to get to the most obvious here. 1 times U equals U, the identity. So there is this thing called the number 1, which gives us back the original vector. Well, 1 is an element of our scalar field. Very important element of our scalar field that we already have. So again, the fact that you have a scalar field at all, the fact that you have scalars already tells me that there's this, that this is true. So everything here is pretty obvious if you just tell me you have scalar multiplication and vector addition. So that's what I want to sort of drill into your mind, is that, you know, it's very easy to get confused about, oh, you have these 10 requirements for vector space. It seems very confusing. Why would you do this? But the focus is really on these 2 things: scalar multiplication, vector addition. All right, now I want to talk about, to finish it up, I want to say, what is the power of approaching things this way? Now, the power of approaching this vectors in this manner is not going to be useful for game development. But I said earlier, this isn't really about, the way I'm explaining all this is not focused just on game development. It's arming you with the understanding of this so that when you go out there and look for information about vectors, you're not totally confused. Because if you don't know this stuff, then just looking at the Wikipedia article on vectors is going to be incredibly confusing, I guarantee you. So it's useful just to know this stuff, because I think there'll be a tendency, if you don't know this, there'll be a tendency for things to seem more confusing than they are. So maybe I should make a new thing, but I'm just going to write here in this little black area. We have more uses now. So we started with this naive viewpoint, very geometric viewpoint. But now that we've defined things in the way that we have, there's other things that are vector spaces than just this geometric picture. For example, polynomials. Sorry that my writing is so slow. Got to figure out how to have a better system here. Polynomials. So for example, f of x equals, I'll just write an example, like x cubed plus 2x squared plus 4, for example. That's a polynomial. Things like this. And if we had another polynomial, g of x equals, I want to be simpler here, so let's just say x to the 5th It could be any polynomial. We can add these. Well, let's say h of x. We can add them, f of x plus, let's say we define it this way. But it makes sense to do this, to add them. And if you analyze it, everything we said about these 10 requirements for vector space will apply to this polynomial addition. So here I'm defining addition in the vector space. And scalar multiplication is simple. Just you can take this polynomial and multiply it times a scalar. No problem. I guess we need closure, so we can say, so maybe a third, maybe we should also say closure, like maybe it's worth thinking about closure. But again, this comes so automatic to me. I don't really think about it. But so we just need a general definition of a polynomial, which exists, like so. It'll you can look these up. It's always kind of annoying to write out. But for example, it'll have some coefficient for, let's actually go like this. A sub, I'll just do a sub 0, x to the n, plus a sub 1, x to the n minus 1, plus dot dot dot, plus a sub n, x to the 0. Okay, there's some general definition of a polynomial. You can look it up. If it sounds bonkers to you or something, just look it up. And we define our polynomials as elements of this set. So it's almost like the more complicated thing is just defining the set that we started with. Remember, we have to start with a set. But intuitively, this is not complicated. Intuitively, it's just you have a polynomial, you can add them, and you can scalar multiply. And it gives you closure. You don't combine those operations, those two operations, and then get something new that's not part of what you were talking about to begin with. What we were talking about to begin with is the set of all polynomials. So we can add them, and we can scalar multiply them, and we always get another polynomial. And that kind of brings up an interesting concept called a linear combination, which is a really super important, it's super important terminology in math and physics, linear combination, where what I was just describing, I kept saying like all the combinations of scalar multiplication and vector addition. I kept saying that. And we want to talk about that so often that we have this fancy phrase called linear combination. So I'm just going to get rid of this and fill it in. Okay. So linear combination. So if we're talking about, for example, a two-dimensional vector space, so 2 dimensions, because that's an easy example. Let's do 3 dimensions. Let's do a 3-dimensional vector space. A linear combination, for example, is, I'll just write it out. These are just arbitrary letters that I'm choosing, where A, B, and C are scalars here. You can choose what kind of, you see this written in all using all kinds of different letters, Greek letters, whatever. These are elements of the scalar field. So I'm just going to say, I'm going to write it in English because it's going to be simpler. Scalars And your x, y, z here are vectors. I'll write the little vectors. So this concept of a linear combination is basically, it's just a vector. We have some amount of x, some amount of y, some amount of z. Again, I need to write the vector things, but it will get a little messy. So you combine some amount of some amount of x, some amount of y, some amount of z, and that's a linear combination. So we say that every vector in the vector space can be expressed as a linear combination of the basis vectors. So that's a very important sentence. So I'll say it again, and you might not need to go back and listen several times for it to make sense. Every vector in a vector space can be expressed as a linear combination of the basis vectors in the vector space. If you're not familiar with the language of linear algebra, that sounds like a bunch of word salad. But it's actually a very simple statement. So this concept of a linear combination is going to come up quite a lot. And it's simple, but it's just the lingo that people who are familiar with linear algebra that they use. And it's very important. Linear combination. Okay. And so we talked about polynomials. I think there's another example is, well, matrices themselves form vector spaces. You can add matrices, and you can scalar multiply them. However, that will get very confusing because later we're going to talk about, matrices, we haven't even talked about matrices at all. Matrices are the objects that we use to transform vectors and also vector spaces themselves. So it'll be another video about matrices. I'll just say kind of from an intuitive standpoint, matrices you can think of them as transforming space. And that's why all of this is really so important, is that there's all kinds of ways that we want to transform space. And if we're in a game, we want to translate things. For example, you want to move the camera. Okay, that is a transformation of space, because normally it's much simpler. The math is much simpler if you keep the camera fixed and you move the world around the camera. So every object in your world is going to undergo a translation. So that's a kind of transformation of space. So the study of these transformation of spaces, that includes rotations and scalings and other things. We want to study the ways in which we can transform space. And if we can kind of master that, we want to sort of master the whole transformations of spaces and all that. And so this linear algebra and the study of vectors and matrices it's the road we're going to go on in order to master these transformations. In particular, we're only going to be studying what are called linear transformations. So it's not every possible transformation. Like I was saying before, I'm not going to write out the whole word, transformation. Like I said before, mathematicians choose their definitions carefully, stuff we've learned from many, many years of history, in order to sort of extract the essence of certain things, and so that we can find very useful patterns and certain structures that are of particular interest. If you found the most general possible object in math, it actually might be so general that it's very hard to extract any interesting content from it. There's actually this is just for fun, but there's a object in math called a magma that came up once when I was in my studies, and this concept of a magma is so general that it almost doesn't mean anything. It's like, I forget what the definition is. It's just like, it's basically just a mathematical object. Like you'll never really see anybody talking about it. unless they're super interested in sort of the foundations of math, I guess. Okay. So matrices themselves can form a vector space, but actually, yeah, I shouldn't even talk about that because it will get confusing, like I said. There's another vector space I want to talk about, but I can't even remember. But, so in quantum mechanics, I'm not going to go deep into this at all, quickly mention it. In quantum mechanics, it's all about linear algebra. It's all about vectors and vector spaces, and your basic objects in quantum mechanics are wave functions. And so they're basically functions. So it's very reminiscent of this stuff, but they are vector spaces. They're complex vector spaces. They use the complex numbers as scalars. But so in quantum mechanics and physics, we're using this linear algebra. And so we have, I don't want to get into it any more than that. I'll just leave it at that, that this is super foundational in quantum mechanics. You need to know what a vector space is. That's a prerequisite. Okay, I can't remember if there's another vector space that I wanted to talk about, but you can see already in the example with polynomials, and if you're familiar with matrices, I'll write that as also as an example for now. It is an example. There's nothing wrong with that. Yeah, so matrices and polynomials are other examples of vector spaces. So you can see that by having this definition, it sort of expands our horizons into other things. And then probably the last thing I want to say today is that there's a theorem in linear algebra that how should I explain this? Basically, I'll explain it casually first. If you tell me that you have, for example, let's say a 5-dimensional vector space, basically this theorem tells me that all 5-dimensional vector spaces are basically the same as all other 5-dimensional vector spaces. So the fancy language that we use is we say that they're isomorphic. Iso meaning same, morphic meaning form or shape. So same form, basically the same structure. So we can talk about vector spaces in general. So for example, there's this 2-dimensional vector space that I talked about earlier. If I wanted a 2-dimensional vector space of polynomials, I need to restrict myself not to have this general definition I gave you is an infinite dimensional vector space. So maybe we want to be more specific. And if we want a 2-dimensional vector space of polynomials, I'll just do I'll index it even though I don't really need to. Let's do x equals, let's say a times x plus some constant c. So our let me just use different letters. I don't know. Doesn't really matter, but I think it'll be less confusing. Big A is our function, and it'll give us, you know what, I'm just going to use a totally different letter, S. Doesn't matter. Sx plus c. And so what we have here now, we have a constant number, and we have some scalar multiple of x. And so this is a 2-dimensional vector space. It's a 2-dimensional polynomial vector space, but we're restricting ourselves to just the constant c and some scalar multiple of x. So a 3-dimensional one, you could actually choose, we could just choose like x to the 5th, but just to be kind of more choose something more logically obvious, let me also stick with the letter S. I'll just say S2 times x squared plus S1 times x plus C. There's different, so this is, do you see that this is three-dimensional? We have some amount of our scalars, okay, just a constant. We have some amount of that, we have some amount of x, and we have some amount of x squared. So we can define this. For example, we can put the C up here, S1, S2. This is our vector. In other words, you need three parameters, or it has 3 degrees of freedom. And I want to show just another very common notation. It's exactly the same thing, but you might see, for example, a sub 2 times x squared plus a 1 times x plus a naught. Just a naught. A naught is just a 0 in the index there. So exactly the same thing, just different notation, just making things, I'm just showing different ways of writing things so that it doesn't come as a surprise later at some point. So this is a three-dimensional vector space. Yeah, that one's three-dimensional, this one's two-dimensional. Now, here I'm using polynomials, but the point is that it doesn't matter what you're talking about. Basically, any two-dimensional vector space is basically the same thing as any other two-dimensional vector space. There's nothing new in the structure. There's nothing new that you can say about them that you can't say about the other. There's nothing new in the structure, or there's nothing new there. So I'm sort of paraphrasing and using ordinary language here. But yeah, there's a theorem in linear algebra that any, let's say, k-dimensional vector space is isomorphic to any other k-dimensional vector space. So I hope that doesn't sound confusing. So if you tell me you have a 7-dimensional vector space, I know that I don't need any new information about your vector space. Like, it doesn't matter if you're talking about polynomials or quantum wave functions or apples and bananas, or like you could have 7 different types of fruit. And so, for example, you have some amount of apples, you have some amount of bananas. That's a 2-dimensional vector space. That's kind of getting somewhere at the essence of why we're even talking about this. You have these apples and bananas are 2 separate things. The x-axis and y-axis, they're 2 separate things. There's no such thing as part x and part y. If there is part x and part y, it's just these linear combinations. It's elements of the vector space itself. That's as far as we can go. You can have half an apple and half a banana, but there's no banapple, there's no anana or whatever. There's some amount of apples, some amount of bananas. That's it. What would be a good C fruit, I guess? Let's go outside of fruits and say carrots, I guess. Now we have a 3-dimensional vector space. See, it's really kind of simple, but I guess whether this is simple or complicated just it depends on your point of view, I guess. So if I'm talking about apples, bananas, and carrots, and I have linear combinations, now, of course, normally you wouldn't talk about negative amounts of apples, but let's allow it. Let's say you could also have a debt. You have a business, and you could actually owe apples, bananas, and carrots. Then that allows us we need those negative numbers, right? And so, yeah. So I'm talking about my business and apples and bananas and carrots, and you're talking about a 3-dimensional vector space of polynomials. It doesn't really matter. Everything, all these 10 requirements, it's all the same. Scalar multiplication works the same. Vector addition works the same. Closure works the same. And yeah, again, all these 10 requirements, it's the same thing. So those three vector spaces, or sorry, those two vector spaces are isomorphic. They have the same structure. And doesn't matter. It's almost like these vector spaces are identical. That might be, that language is going too far, right? Because polynomials are not the same as apples, bananas, and carrots, but they are isomorphic. Now, one day maybe I'll give you the technical definition of isomorphic, but I think it's good enough for now just to have this kind of idea in mind. So that's a very important thing in linear algebra, and it's sort of the power that comes with this language. When people throw around the word vector space, or when they throw around the word linear combination, I immediately have this various ways I can think of these things. I could think of them in terms of polynomials. I could think of them in terms of these pointers, where all these pointers have the tail starting at the origin. Now, I didn't really talk about why we need the tail at the origin. It has to do with the zero vector. This only makes sense. This whole framework only makes sense if the tail of the vector goes from the origin. Maybe if someone has a better way to explain that, put it in the comments. I'm running out of steam here, and I don't really have a better way, anything deeper to say than that. Yeah, I think that's enough for now. Let me know any questions you have. Thanks. Take it easy.